This is National Geographic Channel presents. In a remote part of the Sahara Desert, mysterious chunks of yellow-green glass litter the sand. The ancient Egyptians knew it was here and used it in some of their most precious jewelry. But this desert glass is a mystery to science. How did it get here? How was it made? Now scientists think they've linked this glass to a devastating explosion that occurred here. The kind of catastrophe that could happen again. An international team of scientists is on a mission in the great sand sea of the Egyptian Sahara Desert. They're looking for evidence that will help unlock the mystery of how the desert glass got here. One scientist, Mark Boslow, thinks he may have the answer.
It's a scientific mystery because it's unique. We don't know exactly what the process was that caused the creation of the glass. We know it's a natural phenomenon, and therefore it requires a natural explanation. It may be a very unusual event, but it's certainly not a mystery that can't be solved.
Boslow and his colleagues have developed a dramatic new theory to explain how the mysterious glass was produced. And he has a terrifying vision of what happened here. The details of his theory are still sketchy, but he hopes the evidence in the desert will give him a clearer picture. Egyptians must have known about the glass for thousands of years. In 1998, a discovery at the Egyptian Museum in Cairo made scientists more determined to solve the mystery. Italian scientist Vincenzo Di Michele was looking at gems and semi-precious stones used by the ancient Egyptians. Then, while viewing the Tutankhamun exhibition, he noticed a piece of jewelry hidden away in a dark corner. This necklace of Tutankhamun's is made of different colored gems. But it was the carved yellow-green scarab in the center that caught his eye. The scarab was said to be made of a mineral called chalcedony, a fairly common semi-precious stone. But Di Michele was not convinced. Surrounded by armed guards and museum officials, Di Michele was allowed to examine and test the jewel. He was assisted by local geologist Ali Barakat. Tutankhamun's necklace was carefully removed by the museum's curator. Using a refractometer, Di Michele measured the scarab's optical properties, the refractive index. Every mineral has a specific refractive index. The test revealed that Di Michele was absolutely right. The scarab was not a semi-precious stone. It was, in fact, made of glass. But it was not a glass like any other produced by the ancient Egyptians. Its color, its purity, everything about it set it apart. The tests convinced Di Michele that the glass wasn't man-made. So what was this glass, and where did it come from? Since Di Michele's remarkable discovery, several scientific teams have traveled to the Great Sand Sea to try to find answers, to explain the origin of this unusual glass. Now a new team is trekking to the remote area where the glass was originally found. It's a difficult 3-day drive through the desert before they can even start looking for any glass. Physicist Mark Boslow has never been to this desert, so he relies on geologist Ali Barakat and geochemist Christian Kerbel, who, like Barakat, is an old desert hand. They hope to find fresh evidence of the mysterious event which must have taken place out in the desert.
We scientists have been interested in these desert glasses for a very long time. It's just such a mysterious glass. They have a color and this pure silica composition that makes them really unique in the world. We know no other natural glasses that look like this or have a composition like this. And so we scientists are still kind of puzzled how these things formed.
What puzzles scientists is that this desert glass is not like any other natural glass found on Earth. Most natural glass is volcanic in origin. Volcanic glass forms when hot, molten magma solidifies rapidly, usually when it meets cold water. Volcanic glass is relatively common, but its chemical composition and dark color are quite different from the desert glass. There is another way natural glass can be produced, by an event more dramatic than a volcano, a collision with an extraterrestrial body. When a large meteorite hits the Earth, the intense temperature, pressure, and rapid cooling can turn the ground into glass.
There are glasses that form by meteorite impact, and we know these. There are, for example, these glasses here, they're called tektites, and they are thrown away from impact by hundreds and even thousands of kilometers from the crater. But these glasses are very different in appearance and shape and size from the desert glass that we have here.
The glass appears not to be volcanic, nor is it like any other known meteoritic glass. In fact, it's unlike anything found on Earth. There have been many theories to try to explain what it's doing in the desert. One theory suggests that this area was once a swamp, and that the glass was left behind as sediment when the swamp dried up. A key to this theory is that the glass formed slowly at low temperatures. For years, this premise intrigued scientists.
When I first heard about this idea, I thought, well, it's an interesting one, that it forms at low temperature. But I wasn't quite convinced that the desert glass really formed this way.
To test the theory, Kerbel decided to analyze the glass to establish at what temperature it had actually formed. For help with the study, he went to the Natural History Museum in Vienna, where one of the world's largest collections of meteorites is housed. Using the museum's electron microscope, he examined the desert glass for a mineral called zircon. Zircon is remarkably stable, but starts to disintegrate at high temperatures. Kerbel looked for zircon crystals with light and dark patches. These patches show that the zircon had begun to disintegrate.
And what this tells me is that the glass formed at a very short time and a high temperature. And to understand exactly which temperature we're looking at here, I need to analyze the different bits inside here.
In the dark patches, the zircon is broken down into a form of silica. The amount of zircon left in these patches shows how far the process of disintegration has gone.
In the darker areas, we have less zircon and more silica. And what this tells us is that this little zircon crystal has decomposed partly because of the high temperature, but not completely. And the ratio of the two elements tells me that the temperature was about 1,800 degrees Celsius.
And that's hot, extremely hot, nearly 3,300 degrees Fahrenheit. Volcanic lava is only about 2,000 degrees Fahrenheit. Whatever happened here, the heat it produced was phenomenal. What Kerbal found convinced him and other scientists that they had to look for another explanation, an extraterrestrial explanation. And there was only one thing that they knew of that could create such a shockingly high temperature that it melted the ground. A meteorite impacting with Earth.
Tons and tons of this material falls on the Earth every day, and most of them are very small, just like dust. Some of them are pebbles, and they make shooting stars in the atmosphere. And sometimes a really big meteorite hits the ground at very, very high speed. Melts the ground, it vaporizes the ground, and these high temperatures and pressures are enough to melt a huge quantity of rock.
And even though the desert glass is so different from other meteoritic glass, Kerbal thinks it must have been formed by a meteorite. National Geographic Channel Presents will return in a moment. We now return to National Geographic Channel Presents. Kerbal hopes to find evidence of a massive meteorite impact on the ground. The team still has another day of driving before they can even start looking for any glass or any other signs of what occurred. They are now in the heart of the Great Sand Sea. It's one of the most arid, inhospitable places on Earth. No one lives here. It can be 10 to 20 years between rainfalls. Extreme even for the Sahara.
Yeah, the glass area is all this area. We'll camp at the end of the rocks and the sand here. Right. Like that, we'll make the camp sort of in the middle of the high concentration of the big glass and the black.
You want to be in the second.
There are no roads, no tracks. The massive parallel sand dunes stretch for hundreds of miles. Each dune is a challenge, and without highly skilled drivers, the cars could easily overturn as they slide down the soft sand. Very few people who venture into this part of the desert dare to tackle these dunes, preferring instead the safer route, driving up from the south between the sand ridges. The team has chosen the quickest route, even though it means crossing an endless series of dunes. At last, they approach the area where the glass was originally found. One of the mysteries about the glass is that it's scattered over an area as big as Delaware. The glass is not thick on the ground, but pieces can be found scattered between the dunes.
I'd seen pictures of the glass before, but the first time I reached down and picked up a piece and held it up to the sun, it was very exciting.
No one knows exactly how much glass is in the desert. Estimates range from hundreds to thousands of tons.
Oh, here's a piece. Oh, look at this. There's a nice one. And another one. So this is an area, and look down here on the ground. You can actually see it. If you look here, you see the nice pieces lying around here. There's a piece here. There's a piece there. There's a piece over there.
Most of the glass lying on the surface is small and round, sandblasted and polished by the sand and the wind. Some pieces are buried and are larger and rougher.
This one here is mostly pitted and dull because it has been sitting underground, and only the nice, smooth, shiny part was exposed to the sand, and underground it has been etched by water over hundreds or even thousands of years.
The sand dunes are moving at an astounding 10 yards a year, so new pieces of glass are continually being uncovered. And although there are no obvious signs of a meteorite impact, Barakat thinks there is some evidence. A large meteorite smashing into sandstone should leave behind clues. Under the microscope, the tiny grains of quartz from which this sandstone is mostly made are usually clear inside. But Barakat and others have found samples of the sandstone in which some of the quartz grains have distinctive lines caused by shock waves from an impact. The new evidence makes more solid the theory that a meteorite produced the desert glass. But there was still an obvious problem with the theory, and it was a big one. A meteorite impact should leave behind a crater, but no one has ever found any trace of a crater in the area where the glass is found. The answer to the mystery of how the glass ended up in the desert seemed as far away as ever. For Kerbal, his discovery left him with no doubt as to the origin of the glass. Most of the glass is completely clear, but a few pieces are not.
There's glass, yeah. There's a nice little piece.
The ones that show clear,
yeah,
white, and black,
yes,
all in one piece.
Yeah.
The pieces of glass with black streaks of material inside are crucial to Kerbal's theory. In order to determine what the material trapped in the glass was made of, Kerbal takes it back to his lab in Vienna. To analyze it, he bombards the black bits of the glass with neutrons. He finds small traces of the exotic element iridium.
Here are the peaks that indicate the presence of the element iridium, and this is something we would not expect to find in rocks on the surface of the Earth, and this is characteristic for meteorites. So here we have very good evidence that a meteorite really hit the Earth and was incorporated with the glass when it formed.
But finding iridium is not conclusive evidence of a meteorite. Then, after over a year of searching, Kerbal finds another tantalizing clue, the rare element osmium.
The results are absolutely exciting. We see that the abundance of the element osmium is about 50 to 100 times higher than what we would ever find on the surface of the Earth. And more importantly, the ratios of the isotopes of osmium are very different from surface rocks of the Earth. They are clearly extraterrestrial and show that a meteorite hit the surface of the Earth in the sand when the desert glass formed. So we have a eureka moment here. We now know there was a meteorite impact.
When Ancient Asteroid returns on National Geographic Channel presents. Kerbal is now totally convinced that a meteorite was involved in forming the mysterious desert glass. For him, the lack of a crater isn't a problem. He has a simple explanation. The crater has simply disappeared with time.
I think what we're looking at is probably a very deeply eroded structure. A fresh young crater looks maybe like this, and it is filled in here with broken bits of rock and melt and so on. But with time, all this disappears, and all that we might have left is this central area here, which is very difficult to detect.
But a meteorite large enough to scorch and melt such a vast area of ground had to be big. And even if the crater had been eroded, there is one possible way to spot it. by looking at it from space.
2, 1, booster ignition, and liftoff.
Farouk El-Baz is a remote sensing scientist. He's head of a lab in Boston that interprets pictures of Earth taken by orbiting satellites. He's been looking at satellite pictures from space since the 1960s. At that time, only about 20 impact craters had been found.
With the advent of satellite images from space and the fact that we're going to be recognizing all of these circular features, we now have at least 200 that are proven or semi-proven impact craters.
One reason that there are not more known impact craters on Earth is that some are so big they can only be spotted from space. And the older they are, the harder they are to find.
It is really important to look for a crater that has the right age for the formation of this glass, because if we say that this glass is of meteorite origin, which is most likely, then there should be a crater of that age that would have formed that glass. So these things must come together.
To help El-Baz in his search, he needs to know when the glass was formed. One technique for dating is based on the rate an isotope of the element uranium decays. By counting the tiny scratch marks left by the decaying isotopes, scientists can deduce the mineral's age. Using this technique, the team calculates a date for the desert glass. It was formed nearly 30 million years ago. But is it possible to find a 30-million-year-old crater?
It's not really a problem in this part of the world to locate a 20 to 30 million year old structure, because no matter what the erosive processes were like, you still have in the subsurface the imprint of that impact. For instance, we have the structure here in Chad that has been dated to be older than 200 million years, which means that anything that is 20 or 30 million years would certainly be visible.
So El-Baz and his team begin searching the area for evidence.
We have some craters in here, a tiny one in here, larger craters in south of here, but nothing in that zone that can be called an impact crater. So here is the Great Sand Sea and the dunes going down southward this way. And the silica glass region is right here, and it is a little too far from any of the impact craters that we have formed around. So we conclude from that we have not really found the smoking gun for the silica glass in the Western Desert in Egypt.
While studying the satellite images, El-Baz spotted a circular formation that he thinks deserves closer inspection. El-Baz decides to make his own expedition to the desert to see if the evidence on the ground indicates this is the missing crater. The formation he targets is 60 miles from the main concentration of glass. The team is doubtful that this is the source of the occurrence. But if there's no crater, what can explain the enormously powerful cosmic event that happened here nearly 30 million years ago? Mark Boslow has developed a theory which could solve this seemingly impossible puzzle. The theory started with a catastrophic event, not in the desert, but in a place called Tunguska in the forests of Siberia. In 1927, a Russian scientific expedition visited Tunguska to investigate a massive explosion. The explosion had actually occurred in 1908. But Tunguska is so remote, it was nearly 20 years before they were able to see what had happened. They were astounded at the scale of the devastation. The blast had destroyed more than 80 million trees. Scientists were baffled. What could have caused such an enormous explosion? At first, they speculated that it was a meteorite, but they couldn't find a crater. And when they searched for fragments of a meteorite, they found nothing. The scientists recorded their findings, but no clear theories emerged. For years, the Tunguska event was a scientific mystery. Scientists have had many theories about this event. One commonly held belief is that an extraterrestrial object somehow exploded about 5 miles up in the atmosphere. This mid-air explosion, or aerial burst, would have been equivalent to about 20 million tons of TNT. Over 1,000 times bigger than the atomic bomb dropped on Hiroshima. Is it possible that a similar but much bigger aerial burst generated temperatures hot enough to melt the ground and turn it to glass? There is one place in the world where it's known that an explosion created a layer of glass. The Trinity site in New Mexico is where the world's first atomic bomb was detonated. Sergeant Ben Benjamin was part of the official photographic team. He was just 22. Cameras were set up at several locations. Benjamin was in a concrete bunker 6 miles from the blast site. For him, it was an awesome, almost surreal experience.
We didn't know what was going to happen here, and we were all concerned. There were rumors that this was going to be a dud, and there were all kinds of rumors of strange things that might happen.
At 5:29 on the morning of July 16, 1945, the bomb exploded.
We had a PA system. They were counting down in seconds, and when it came to -10, I switched on all 4 cameras, and it went off, and it was incredibly bright. It was absolutely fantastic. It filled this valley with a light that no one had ever seen before. It turned out to be 20-some times the brightness of noonday sun. And my God, it was the most amazing thing that I had ever seen in my life, and I'll never forget it.
A mushroom cloud burst into the sky with the force of 20,000 tons of TNT.
Along with the light came this blast of heat. Felt like opening the door of a furnace and having the heat warm you instantly, even here at 6 miles.
A week after the explosion, Benjamin was allowed back onto ground zero. What he saw was startling.
And of course the whole tower that the device was on, all that steel, tons and tons of steel, was absolutely vaporized.
The bigger surprise was what had happened to the ground.
It was covered with green glass, the melted sand here. All the sand had melted on the top, the first quarter inch or so. This green glass was covering the whole entire area, and it was cracked, and but one could walk on it, and you'd crunch. You'd be walking like on a field of maybe ice.
The sand was transformed into a thin layer of glass covering an area 600 yards wide. But the Sahara Desert glass area is thousands of times larger.
From here we go down another about 10 or 15 kilometers and we find still some glass, and we go up about another probably 30 kilometers even and we find glass. But we're very close to the center of the area where we have the glass around here.
If such a large area of glass was formed as the result of an aerial burst, it must have had the power of many thousands of atomic blasts. A natural blast of that magnitude was completely unheard of. No one had any idea how such a devastating blast could have been produced. This is where Boslow's expertise comes into play. At the Sandia Labs in New Mexico, he's developing a computer model to see if the airburst theory can be right. An event in 1994 was the turning point, the impact of the comet Shoemaker-Levy with the planet Jupiter. When the comet went into orbit around Jupiter, it broke up into over 20 fragments. Then, one by one, these fragments hurtled down into the Jovian atmosphere. Nothing like this had ever been seen before.
I think that the impact on Jupiter was really one of the most exciting things to ever happen in the history of science.
Boslow studies the physics of large impacts by using computer simulations. For Boslow, the Shoemaker-Levy comet was the biggest, most exciting experiment imaginable.
This was a real opportunity to see something that we couldn't see in the laboratory, something of a scale of a magnitude way beyond anything imaginable, beyond our wildest dreams.
Boslow's team came up with a new theory, predicting that the impact of the comet would produce a massive fireball.
This is a sequence of snapshots from our simulations. The top image shows this incandescent fireball rising over Jupiter's horizon to be seen from Earth. And in subsequent frames, you see this fireball growing and cooling, but growing into this enormous plume to very high altitudes. It just gets huge.
When the fragments of Shoemaker-Levy smashed into Jupiter, the pictures from the Hubble telescope were just as spectacular as the simulation predicted.
When we saw the Hubble Space Telescope images for the first time, we were so excited to see this spectacular plume rising over the horizon.
Their predictions were remarkably accurate.
These are actual observations, snapshots from the orbiting Hubble Space Telescope. In the first image, you see this incandescent fireball rising over the horizon, and in subsequent images, you see it growing into a plume, and it continues to grow to this enormous size.
They predicted that a massive plume of hot gas would be expelled well over 2,000 miles into space.
It was a spectacular explosion. I mean, it was just a tremendously enormous explosion beyond anything anybody's ever experienced in the solar system.
The Shoemaker-Levy impact on Jupiter was a pivotal moment in science, and it made scientists rethink what could happen here on Earth.
So this really was a turning point in my understanding about how impacts work. I and most people thought of impacts on Earth as events that create craters, collisions with the solid Earth, and typically we ignore the atmosphere. We ignore atmospheric effects. Well, the atmosphere is tremendously important, and this is the lesson we learned from this.
Another scientist who paid close attention to the Shoemaker-Levy comet was John Wasson. He's one of the world's top meteorite scientists. Wasson also has an interest in the origins of the Egyptian desert glass, looking in particular at one special piece.
It's special because it has very distinct layers. The layers consist of dense glass, which is almost free of bubbles, and foamy glass, which is full of tiny little bubbles.
Wasson believes the layers were formed by intense heat radiating from above, from an extremely hot sky.
When the thought came to me that it required a hot sky, I thought immediately of the Tunguska event. That's exactly the kind of event that I need. An aerial burst, but many, many times larger than Tunguska. Perhaps 1,000 times or even more times larger.
And the massive fireball produced on Jupiter by the comet seemed to offer another clue.
I thought, how nice. The Shoemaker-Levy comet seemed to me to be ideal for producing an aerial burst and producing desert glass.
This crucial new evidence made Wasson and Boslow wonder, could a similar aerial burst happen here on Earth? To explore the aerial burst theory further, Boslow needed to adapt his computer model to simulate such an explosion, and for that he needed more data. He wanted to see for himself how widely the glass was spread out in the desert.
I think it's helped a lot to see the distribution of the glass, how widespread it is in some places, how concentrated it is in others.
Scientific reports claim the glass is scattered over 2,500 square miles of desert. Boslow doubts that the original area could have been that vast.
Well, it's not clear to me whether the current distribution was the actual distribution when the event occurred.
The Sahara only started to become desert about 7,000 years ago. And over the last 30 million years, there were big rivers and lakes here.
What I think is that the glass was originally at a much smaller area. There were lakes here some time ago, and there was some water, and it transported the glass farther away from the area where it originated.
Boslow was now confident that 30 million years ago, the distribution of the glass in Egypt was smaller than now, but it still needed a massive event to produce it. He fed the latest data into his computer model.
What we modeled is 120-meter diameter object entering the atmosphere at 20 kilometers per second, and we started off the simulation way above where this frame starts.
To examine the evidence of an actual impact found in the desert, the simulation allows a fragment of the meteorite to reach the ground and make a small crater. But such a small impact would not produce the glass. The simulation also shows something far more powerful happening at the same time. Before reaching the ground, the incoming meteorite burns up, leaving a trail of incandescent material in its wake, a massive column of fire, which turns into a fireball.
The widest temperature here is the temperature of the surface of the sun. And as it expands, the fireball is actually pinned against the surface, and it's moving very rapidly beyond hurricane force. So we've got this blast of air that's hotter than the melting temperature of the sand blowing across the sand, so it's melting the top surface, and then that melt freezes to form the glass.
And just like on Jupiter, an enormous plume of searing gas is streaming out into space.
So while all this material is creating this fireball down on the ground level, there's also a plume that's being formed at much higher altitudes, 80 to 100 kilometers above this level, and it's ejecting material out into space.
The simulation illustrates how even a relatively small meteorite can create a fireball hot enough to produce the amount of glass found in the Egyptian desert. And yet the size of the replicated explosion dwarfs the first atomic bomb blast at Trinity.
And what I want to emphasize is that is hugely bigger in energy, hugely more powerful than the atomic test at Trinity, 10,000 times more powerful.
Wasson and Boslow now think they've solved the mystery of how the desert glass was formed in the Great Sand Sea. 30 million years ago, an asteroid was on a collision course with Earth, headed for Egypt. As it began to burn up, it created a hot plume in its wake. Before reaching the ground, it exploded into a blistering fireball. Surface temperatures immediately reached 3,200 degrees Fahrenheit. The ground, which was mostly sandstone, melted and was transformed into yellow-green glass. Above the surface, a column of superheated gas propelled itself into space. The total effect was far more devastating than if it had simply hit the ground. The theory predicts that an aerial explosion is far more likely if an object breaks up easily, like the fragile comet Shoemaker-Levy. But just how common are fragile objects in space? An incident in 1997 proved to be a major eye-opener for the scientific community. A NASA spacecraft flew past an asteroid called Matilda. Matilda's slow rotation showed it was not solid, but was a loose assembly of rock held together by gravity. They call it a flying rubble pile.
We've discovered a number of other asteroids which have similarly low densities, and this has led to a real paradigm shift where now it's accepted that most asteroids probably consist of rubble piles and are extremely weak.
These rubble piles are likely to explode if they enter the Earth's atmosphere. And Wasson believes he has evidence of another aerial burst, this one on a truly cataclysmic scale. He's found glass all over Southeast Asia, Thailand, Cambodia, Laos, Vietnam, and even southern China.
The curious thing about it is no crater has been found. And I think it was a super Tunguska-like event.
Wasson thinks that about 800,000 years ago, a flying rubble pile broke up while on a collision course with Earth. The fragments became fireballs, incinerating everything on the ground within some 300,000 square miles. Wasson's findings caused some to wonder, is there any way to protect the Earth from such a phenomenon? In recent science fiction movies, the solution to a large asteroid hurling towards Earth is to blow it up. According to Boslow, this would only make matters worse.
In those movies, yeah, Hollywood certainly got it wrong. You can't just explode an asteroid just before it hits the Earth and suddenly the pieces disappear. Now you have a lot more smaller pieces hitting the Earth, and they're all making fireballs. You could actually make it much worse by attempting to explode an asteroid just before it collided with the Earth.
Luckily, it could be millions of years before there's another collision with a large asteroid. But a smaller asteroid, like the one that exploded over Tunguska, could collide with Earth as often as once every 100 years. And the next time, it might not be over Siberia. There is a small chance that it could happen over a populated area.
So there would be no warning. If an impact like this were to happen, it's very unlikely that there'd be any advance warning at all. While the probability is small, it's not negligible. It really could happen in our lifetimes. And if it hit in the wrong place, it could be devastating for a city.
In a city like London, millions of people would be killed. The devastation from even a small Tunguska-like fireball would extend over an area 8 miles wide. We now know what happened in the Egyptian desert was even more destructive, and it will happen again.
There are hundreds of times more of these smaller asteroids than there are of the big ones that the astronomers track. There will be another impact on the Earth. It's just a matter of when.